Yeah, so I'm going to be talking about thermalization dynamics in quantum field theories in one dimensions. And this is a talk based on work from last year with Luca. Okay, so the basic starting point was if we have some generic interacting quantum field theory, then what we expect is for it to thermalize. And let me be a bit more specific about exactly what I mean by thermalization for this talk. So imagine we take our field theory and we start in a thermal state at some temperature T. Okay, and then we knock it out of equilibrium, for example, by dumping in a load of energy. Okay, and then there's going to be some complicated non-equilibrium dynamics, and what we expect at the end of the day is this thing finally returns to some global equilibrium state. Okay, and we expect this procedure to happen in various stages. So at very early times, there's going to be some complicated dynamics, which depends on exactly what our quantum field theory is. Okay, but after a sufficiently long time, what we expect is before the system globally equilibrates again, we reach some local thermal equilibrium. Okay, and at that point, we have good effective theories describing what happens in local thermal equilibrium. As we've heard today, theories of hydrodynamics. And then these guys control the kind of final relaxation back to the final equilibrium state. Okay, and so we were interested, or trying to address, two questions in this process. So the first one is, how does this hydrodynamic description emerge from microscopic theory? So, by what process is it that this local equilibration actually happens? How long does that take? And so on. And then secondly, once this hydrodynamic theory emerges, okay, this is some effective theory characterized by lots of coupling constants, the diffusion constant, viscosity, etc., etc. How are those coefficients related to the original microscopic Lagrangian? Okay, and so as I'm sure you all know, in general, answering these questions is really hard because it involves doing quantum field theory at finite temperature and in real time, and that's quite difficult. There are some simplifying limits where we can get a handle on things and make some progress. So one, we've heard today, is if we can think of our state as made up of some weakly interacting particles, and we can hope to use kinetic theory and perturbation theory and so on, and paste these together to get some picture of what's happening at each stage. A different limit is if we have a quantum field theory that's very strongly interacting and has some large number of fields, then certain quantum field theories like that can be mapped to theories of gravity, and then we can answer these questions by doing easier computations in gravity. But what I want to talk about today is a kind of simplifying limit which is complementary to either of these two things, which is to take specifically 1 + 1 dimensional quantum field theories in infinite volume, so just on the line, and consider them in the limit of very high temperatures or very low temperatures. Yeah.
Is the high temperature limit defined for a field theory? I normally think about it as being regulated by something in the UV and not being in the field theory anymore.
So what I mean, I'm going to be a bit more specific what I mean in a second. I mean, I'm going to, maybe if you give me a second, then I'll get there. Yeah, so actually specifically here, I'm going to talk about high temperatures, just for simplicity, but there's a kind of equivalent story at low temperatures, where the details are slightly different, but I'll just focus on high temperatures. Okay, so what is it that's special about 1 + 1D quantum field theories at kind of high temperatures or low temperatures that makes this a nice limit? Well, what's special about them is that in a sense, they're close to 2D CFTs or 1 + 1D CFTs. Okay, and we know a lot about 1 + 1D CFTs, even at finite temperature and even in real time. Okay, so what do I mean by that? What I mean is we can think of our 1 + 1D quantum field theory as a 2D CFT.
Are you assuming Lorentz invariance?
Yes. Yeah. So we can think of a 1 + 1D QFT as a 1 + 1D CFT deformed by some relevant operators. Okay? And I'm going to consider the case where those relevant operators preserve Lorentz invariance. Okay, so what this gives me is a 1 + 1D relativistic quantum field theory. Okay, so what I'm doing is I'm taking a CFT scalar operator, that CFT, O, which is relevant, so it has some scaling dimension between 0 and 2. Okay, it has some coupling constant lambda. Okay, you can see here, that's the central charge of the CFT. So that's kind of unimportant for a lot of what I'm going to say, but in the second half of the talk, I'm going to take a limit where C is large. Okay, so this coupling constant lambda is dimensionful. Okay, in the thermal state, I can make a kind of natural dimensionless coupling by absorbing into it the right numbers of power of the temperature so that it's dimensionless. And what I might expect is, so this lambda bar, this is dimensionless coupling, is that when this guy is small, okay, the effects of this thing are going to be small, and I'm going to have something that basically looks more or less like a 2D CFT. Okay, and so the high temperature limit here, I really just mean this coupling should be small. Okay. So as I said, we know quite a lot about 1 plus 1D CFTs, and something in particular that we know is they don't thermalize, at least in the way I described before. So there's very constrained by symmetries such that this emergence of hydrodynamics never happens. Okay. And that's important because what it means is turning on this small coupling lambda bar, although right, it's small, it does something very important, which is it breaks conformal symmetry, and so it gives room for thermalization to happen. Okay. And in the CFT, since the way to think about it is it takes infinitely long for hydrodynamics to emerge. What that means is when we break conformal symmetry in this weak way, okay, we expect thermalization to happen, but to happen very, very slowly. Okay, and so we can hope to have a controlled description of what's going on by working in this small parameter.
So we say don't thermalize, but I guess it goes to GGEs and generalized hydrodynamics, right, without the constant quantities.
Sorry.
Something like that. Right? So I mean, if it has too many symmetries, but then you can account for these symmetries in your hydrodynamics, right, in the thermalization.
So what I'm saying here is turning on this coupling will break all of those symmetries. So at the end of the day, you're just, in the IR, you're just left with kind of relativistic fluid dynamics. Yeah.
Yeah. But I mean, like near for lambda small, then you have these other tools that you can use, I suppose.
Yeah. Okay, and this slow thermalization happens even when the CFT is strongly interacting here. So that's kind of different than in higher dimensions. You think things thermalize slowly because the particles interact weakly. But what I'm saying here is in 1 plus 1D in this setup, it will always be slow even if there's no kind of weakly interacting particle picture of the CFT. Okay, so what I want to do in this talk is basically just study this theory. One simple non-equilibrium observable of it, which is just the 2-point function of the stress tensor in the thermal state of this QFT. Okay, and the talk's kind of split into 2 parts. For the first part of the talk, I want to start with the kind of early time picture of the emergence of hydrodynamics. Okay, so as I said, we have a CFT, we turn on a small relevant deformation, okay, and we have the small parameter lambda bar, okay, and so at early times, things should look like a CFT, okay, and we can use conformal perturbation theory, which is just perturbation theory in this coupling, okay, and try and see what happens, right, as we break conformal symmetry, what happens as time goes forward. And what I want to explain is that in order for hydrodynamics to emerge, this perturbation theory, conformal perturbation theory, has to break down. Okay, and so the first part of the talk, I basically want to explore, how is it that it breaks down? Right? What processes in this field theory caused conformal perturbation theory to break down, and therefore hydro to emerge? Yeah.
So you're taking C to be large, but C appeared in the numerator with the lambda. So I guess you're taking the temperature to be large enough that despite C being large, the combination is small, or is that unnecessary?
So I'm not taking C to be large until later on.
Okay.
And I'm kind of I'm normal. Yeah, this normalization of my action is basically such that when lambda bar is when C is large and lambda bar is order 1, okay, I get a kind of order of 1 change in my equation of state. Okay, so that's the first part of the talk. then the second part of the talk, I want to kind of switch and study the late time effective theory, which is hydrodynamics, and explore, so once hydrodynamics emerges, what are its properties. And here I'm going to take the extra limit where C is large, so that gives us some extra control. And what I want to explain here is that, so hydrodynamics is a kind of, not really a theory, right? It's a kind of framework with lots of different theories inside it. And what I want to explain here is, in this setup, we can really essentially solve for the hydrodynamic theory that governs the stress tensor two-point function exactly. So what I mean is, we can write down kind of order by order in derivatives every single possible term that is allowed. Okay, in the derivative expansion, so the first one, there's kind of diffusive term, and there's corrections and corrections and corrections. And in 1 plus 1d, we can really write down exactly what they all are. Okay, and they all have some transport coefficient multiplying them. And the second thing that I want to explain is I'm going to give an argument that in the setup and a large C, actually all of these transport coefficients are just universal. Okay, so they depend only on the central charge, this dimension, and the temperature. Okay, and they don't depend at all on any other details of the CFT. Okay, and so we can essentially just write down exactly here's the hydrodynamic two-point function. Okay, to all orders. And then what we can do is sort of push that back to early times where we expect it to break down, right? Because hydrodynamics should emerge at some point. If you push it to an early enough time, it should break down. Okay, and we can see that it breaks down, and we can read off where does it break down. And it breaks down at exactly the same time scale where conformal perturbation theory breaks down. Okay, and so the picture here is that basically hydrodynamics emerges from the CFT. Time scale, which in units of the temperature is a 1 over lambda bar squared, right? So it's very big when lambda bar is small. And it emerges when conformal perturbation theory breaks down. Okay, so starting off, let me talk about conformal perturbation theory. Start off with, before conformal perturbation theory, just some facts about two-dimensional CFTs that I'm going to be using. Okay, so what's nice? One nice thing about 2D CFTs is that the two-point functions of scalar operators like this and the stress tensor are just fixed by symmetry. Okay, so on the plane, so Z is some complex coordinate on the plane. Two-point function of a primary scalar looks like this. The stress tensor in a 2D CFT, you can split it into two parts. Right-moving stress tensor, this left-moving stress tensor. Okay, the right-moving stress tensor looks like this on the plane. Okay, and there's something similar for the left-moving one. Okay. Another nice fact about 2D CFTs is we can do a conformal map from the plane to the cylinder. And what that means is we can compute the finite temperature two-point functions exactly as well. They're just fixed by symmetries. Okay, so at finite temperature, so in the thermal state, the two-point function of a scalar operator looks like this. Okay, and the two-point function of the right-moving part of the stress tensor looks like that. Okay, and basically the important feature of these guys I'm going to be using is that away from the light cone, they're exponentially suppressed. Okay, so if I take, so x minus t and x plus t, these are my light cone coordinates, right? If I take these to be much bigger than the kind of thermal width, okay, then I'm going to get these cinches become exponentials, okay, and the correlations are exponentially suppressed. Okay. For the stress tensor, it's slightly different because the stress tensor is chiral. So this, as you can see, doesn't depend on x plus t, right? It's independent of the distance along one light cone, but it's exponentially suppressed, kind of transverse to that light cone. So those are just correlation functions in the CFT. What we want to do is compute, conformal perturbation theory, so the corrections caused by this coupling that breaks conformal symmetry. And ultimately, we want to compute the two-point function of the stress tensor. So I'm going to start with something a bit simpler, which is still going to teach us something very useful, which is instead of thinking about two-point functions, just something thermodynamic, the free energy or the pressure. Okay, so to compute the pressure, we want to compute partition function on the cylinder with this action here. Okay. Doing this exactly is, usually impossible. So what we're going to do is expand out the exponential in powers of lambda. Okay, and that is essentially going to get the further expansion for the pressure, which is, that is what conformal perturbation theory is. Okay, so first of all, we get the pressure of a CFT. Then we'll get a correction, which depends on the expectation value of O in the CFT. Then we'll get a smaller correction that depends on the 2-point function of O, and so on and so forth. Okay, and so just knowing correlation functions in the CFT, we can compute, the pressure perturbatively outside of the CFT. Okay, and as I said, we know this guy is just 0. This guy here, I had it on the previous slides, and you can integrate it. And what you find is the pressure, like this, and we'll get some power series in lambda bar. That's conformal perturbation theory. Alpha delta is just some complicated looking number, depends on the scaling dimension. Okay, and the only important thing about it for this talk is it is positive. Okay.
So integral d to x should be just dx?
Yes, thank you. Okay, that's the pressure. We can also compute the energy density in a similar way. And once we compute the pressure and we compute the energy density, we can also compute from that the speed of sound. Okay, so what we see here is in the CFT, speed of sound is just 1. Okay, and then when we break conformal symmetry, it gets corrected. Okay, and when lambda bar is small, it gets reduced to something which is close to 1, but less than 1. Okay. And why is this important? Well, it's important if we think about, let's think about our stress tensor 2-point function in space-time. Okay, so as I said before, in the CFT, this thing is supported along the light cone. Okay, if you're more than a thermal distance away from the light cone, it's just exponentially suppressed. Okay. But if our state is going to thermalize, okay, at the end of the day, eventually hydrodynamics is going to come out. We know what the excitations of hydrodynamics are. They're sound waves, okay, if you travel at this speed. And what that means is the stress tensor 2-point function, once hydrodynamics has emerged, right, should be localized not along the light cone, but along this sound cone. Okay, exponentially suppressed everywhere else. Okay. So what you can see here is if I project this up to very, very late times, okay, the hydrodynamic 2-point function, right, is supported in a totally different part of space-time than where the CFT 2-point function is.
I'm sorry to interrupt. Do you know how? This line must be broadening, right? I mean, this. You know by which power it's actually broadening?
It is known, but I can't remember from the top of my head. Yeah. So I don't know if Luca remembers.
The hydrodynamic broadening, you're saying?
Well, I mean, you have a sharp peak, right? I mean, there's sort of this effective in what do you call it, south cone, and then there will be broadening, right?
Yes.
I mean, and then so what power does it broaden?
So
it's
it
a
would
function
be
of time. I mean,
the hydrodynamic mode would be KPZ broadening.
Okay.
But
you see
it's
this
still
in this theory also? Or?
Yes. So not when he takes large C, because that would kill fluctuations, and then it would be diffusive.
Okay. Good.
But the broadening isn't. So they're still very far from each other.
No, very good. Yeah.
Yeah, so what this is saying to us is that if I want to get hydrodynamics out, I can't start with the CFT 2-point function and do some small correction to it, right? There's a big shift here in what happens. Okay, and so what that means is if we want hydrodynamics to come out, right, we want thermalization to happen, what that means is this conformal perturbation theory must break down, even when lambda bar is very small.
Okay, I mean, you can take a theory which has hydrodynamics, which has some sound waves and all that, and then modify it, like the coupling, and of course the sound speed will be modified by this coupling, something like that. And it's the same phenomenon, right? You will also have that, you have a large change of the 2-point function, so you have similar phenomenon as that, right? It's not, I mean, it's more like, it's a general question about perturbation of a theory which may be hydrodynamic theory to give a new hydrodynamic theory, but that's kind of the more general question.
Yeah, so there is a certain kind of sense in which you can think actually, well, despite what I said a second ago, you can think of a CFT as a hydrodynamic theory, and I'm going to come back to that later on. That there'll be a
write
time
out an
when
equation for
that
CFT
useful
and
data
it's
is enough, yeah.
perfectly fine, right?
Okay, so we expect conformal perturbation theory to break down, right? We expect thermalization to happen in general, so we expect conformal perturbation theory to break down in general, even when lambda var is very small. So now what I want to turn to is, does that happen, right? Can we see how that actually happens? Okay, so now what I want to compute is really the two-point function of the stress tensor. Okay, so here I'm going to compute the retarded two-point function, okay? And I'm going to pick the right moving component of the stress tensor. Okay, and in 2D, we can get all the other components of the stress tensor two-point function from four identities, right? Once we know this one. So this really tells us all we need to know. Okay, so technically, I'm going to do this in a slightly different way than I did conformal perturbation theory a second ago, but the basic point is the same. We want to compute corrections to the CFT result in powers of lambda squared. Okay, so what I've written here is we can use word identities to write the two-point function of the stress tensor in terms of the two-point function of the scalar operator in this way. Okay, and I split this into two lines. So the thing on the first line is basically the two-point function of the stress tensor in the CFT. Okay, so it's got some poles, omega equals k, right? And if you really transform this, this is just telling you the retarded two-point function only has support along the right light cone. Okay, in particular, if I Fourier transform this guy here, I just get derivatives of this delta function. Okay, and it's the thing on the second line that contains all the interesting corrections. Okay, so first, what I'm going to do here is compute not all of the corrections, but just the first correction, right, the lambda squared correction. Okay, and that's the reason why this formula is useful. So I have a lambda squared here. Okay, so if I want to compute, right, the first correction in powers of lambda squared, I can just evaluate all this stuff here in the CFT. Okay. And the important term is going to be this one here. Okay, multiplied by these things here. Okay, so what I want to do is think of this thing here as the product of three different two-point functions. Okay, I've got two powers of omega plus k over omega minus k, right? Which is essentially, if I Fourier transform this, is going to be like a convolution of two two-point functions of the CFT stress tensor. Okay, plus a convolution of the CFT scalar two-point function. Okay, so yeah, this is what's written here. The important order lambda squared correction is that. Maybe if I, on the next page, I have a picture, right? I basically have a stress tensor two-point function propagating from the origin to some point x1, t1. Then I have a scalar two-point function propagating to some other point x2, t2. Okay, and I have a stress tensor propagating out to the kind of final insertion point at tx. Okay, and this correction, right? So we can just this integral I had a second ago, right? We can just do this, but before doing it, let me explain the kind of important features you get by doing it. So the first thing we can see is that this correction, what it's going to do is it's going to cause the two-point function, instead of just being localized along the light cone, to spread, okay, up to a distance 1 over inside the light cone. Okay, and that's just because the scalar two-point function, okay, it's not exponentially suppressed, right, when these guys are separated by distance up to the inverse temperature. Okay, so this thing here is going to push some signal inside the light cone. Okay, the second thing we can see about it is it's not going to decay even at very late times, right? And the reason for that is the stress tensor propagator, right, which takes us out to very late times, doesn't depend on a distance along the light cone. Right? This is a chiral guy, so it's not suppressed, it just propagates freely along there. Okay, and in fact, not only does it not decay at late times, in fact, this correction is going to start growing at very late times. Okay, and the way we can see that is that these two scalars, right, so we insert our two scalars at some point, x1, t1, and x2, t2, right, and at the end of the day, we're integrating over the positions of those two scalars. Okay, but since the stress tensor two-point functions don't depend where we are along the light cone, what that means is, as long as I insert these guys close to each other, thermal distance apart, I can insert them anywhere along the light cone, okay, without changing the value of the integral. Okay, And since I'm integrating over where I insert them, integration basically gives me an extra factor of t plus x here. So this is where so this is what you get by just evaluating that integral, and this is where it really comes from.
But there's exponential suppression with the siege, right?
Yes, yeah, so maybe if I go to the next slide. So now if I want to compare, so this is the first perturbative correction. Now let me compare the size of that to the size of the leading order one, right, which also has the same kind of exponential suppression. So let's look at kind of up to a thermal distance inside the light cone and at very, very late times. What I'll find is a correction, right, relative to the leading order piece, right, is not lambda bar squared, but it's lambda bar squared multiplied by the time. Okay. So what it's telling me is that even when lambda bar is very, very small, right, if I wait long enough, this correction is going to get big. Okay, and that's good, right? We expect things to break down even when lambda bar is very small. Okay, and this is how that happens. Okay, and so what it suggests is that conformal perturbation theory indeed breaks down at very late times, right? And we can tell what time it is that it breaks down at. It's this time, or we would expect it to break down at. It's this time.
So this two-point function of t, does it obey some fake hydro equations, or is it?
You mean including this one correction, or you mean this?
Yeah, including the correction. Like before you hit this breakdown time. Like after the breakdown time, you're going to talk later, but before you hit the breakdown time, is there some kind of fake hydro?
I don't know. So without the correction, the CFT two-point function obeys a kind of hydrodynamics. With that correction, yeah, I'm not sure. Yeah. Okay, so that was just the first correction, right? In theory, what we like to do is then compute all the higher corrections and show that, right, this isn't just some fluke about the first order correction, but really this is happening order by order, and that the effective coupling is not really lambda bar squared, but lambda bar squared multiplied by t. Okay, so we couldn't explicitly do the higher order ones, but we can at least see, where those corrections are going to come from at higher orders. Okay, so if I sort of, I think back to my kind of path integral formulation of conformal perturbation theory, right? If I want to compute corrections to the two-point function of the stress tensor, okay, then order 2n in this perturbation theory, I'm going to bring, each power of lambda, right, brings me down, each higher power of lambda brings me down an extra scalar operator like this. Okay, and so to compute what happens, the correction at order 2n in perturbation theory, what I need to do would be to compute this 2n plus 2-point function in the thermal state of a CFT. Yep.
So the light cone, I guess, is sharp on the other side. So whenever you insert one of these guys, you've got to move in. You can't move back out. Is that right?
Yes. Yeah. I mean, so the retarded 2-point function better vanish outside the light cone because it's a commutator. Yeah. So this is why I always shift you in here. If you like, you can think of this as if I, in the free particle picture, I have some free particles that move along the light cone and they scatter and it pushes them in, and eventually that thermalizes it. One way to think about what I'm saying is that picture is true even when you don't have, weakly interacting particles. Okay, so we need to evaluate this 2n plus 2-point function. It has two stress tensors and then 2n copies of these scalar operators. Okay, and as I said, we couldn't do this in practice, but we can see where the kind of enhancements I just talked about are going to come from. Okay, so first of all, as I said, if the scalar operators are more than a thermal distance apart from one another, what we expect is these correlations are going to be exponentially depressed in the thermal state. And so what that means is, when we insert the scalar operators, we better insert them in pairs. Okay, so we're going to get contributions to this when the scalar operators are inserted in pairs. In space-time pairs. Okay. And we have these two scalar operators. They're close to one another, right? In a CFT, we can use the OPE to see, right, when we push these two scalars close to one another, they're going to create, other operators in the CFT. In particular, what they're going to, they'll create all possible operators, but one thing they're going to definitely create are chiral operators like the stress tensor, product of the stress tensor, and derivative of the stress tensor. Okay, and so we're going to have contributions to this kind of integral, right, which basically look like this picture here, right, when we're going to have kind of order 1 contributions to this integral when two scalars are inserted close to one another, diffuse and produce a stress tensor. That stress tensor can just move freely in that direction. Okay, and we have essentially n copies of the picture I had before, and like before, we can freely slide these pairs up and down here without changing the value of the integral, right, because the stress tensors are chiral. Okay, and yeah, so at each order in perturbation theory, we're just going to get the same effect happening, and we're going to get contributions that scale like this, okay, which is going to telling us perturbation theory breaks down at late times. Okay, and it breaks down, right, because of this exchange of stress tensors.
Do you have some control over the combinatorics? So you can say there's an n factorial or something?
No, so we didn't manage to really evaluate any of these corrections. So what we did see is when you take the limit where the central charge is very large, so really here, this is some horribly complicated multi-point function of the stress tensor. If you take C to be very large, you can see it begins to factorize in a very nice way, so that really you're just getting like 2-point functions of the stress tensor and 2-point functions of the scalar. I mean, as I'm going to come to in the second part of the talk, taking C to be large, I think will give enough control that I believe it's really possible to really do this resummation, but we didn't manage to do it. Okay, and so this kind of picture causes conformal perturbation theory to break down. You know, from the kind of parametrics, it gives you the possible to get the right kind of signal in the sound cone that you expect from hydrodynamics. Okay. So yeah, that's basically this microscopic picture of how these theories are thermalizing. Okay, so in real time, thermal conformal perturbation theory breaks down even when this coupling is very small, and it happens because of this unsuppressed exchange of the stress tensors. Okay, and that is what essentially allowed, right? That's not some weird mathematical artifact. It's telling you something important, right? The hydrodynamics is coming out. Okay. So now what we want to do is move on to kind of trying to examine what comes out. Right? What is this theory of hydrodynamics that comes out? And if we push it back to early enough times, can we see it also breaks down? Okay, so hydrodynamics, what is it? It's basically an effective theory for the dynamics of the stress tensor that we expect to work at late enough times and long enough distances. Okay, and like all effective theories, essentially what we do is we use the symmetries of the problem. So in that case, this is going to be Lorentz invariance to constrain what possible terms we're allowed to write down. Each term comes with some undetermined parameter, which is usually called a transport coefficient, okay, and that is some input to the effective theory. So the second part of the talk, what I want to say is if we take this additional simplifying limit where C is also large, okay, and we're breaking conformal symmetry weakly, we can basically solve for exactly what this is. What I mean by that is not just in theory can we write down the hydrodynamic theory by writing down the allowed terms of the first couple of orders, but we can really write down every single order, every single allowed term. Right? There's kind of comparatively not very many of them in 1 plus 1d. Okay, and then I'm going to give an argument, so not a proof, but an argument that relies on one assumption, that all of the transport coefficients here, actually there's just a universal expression for them, and they don't depend on very, very little details of the microscopic theory. Okay. So this is essentially relativistic fluid dynamics in one plus one dimension. Okay, so what are the degrees of freedom? Well, the assumption is that at late enough times, right, the only degrees of freedom of matter are the fluctuations of conserved charge densities. So I'm assuming in our case that is the energy and the momentum, right? So I'm assuming this is not some integral theory or anything like that. Okay, so those are basically components of the stress tensor, and to make things Lorentz covariant is more convenient rather than working directly with the stress tensor to work with a fluid velocity and a temperature. Okay, and the equations of motion are that the stress tensor is locally conserved. Okay, and so what I need to do to specify my effective theory is to write down an expression for the stress tensor in terms of my hydrodynamic variables, so in terms of fluid velocity, temperature, okay, and I'm also going to include here a space-time metric. Okay, so I'm going to allow my fluid not to live just in Minkowski space, right, but to live in some manifold with some general metric, and that's useful because if I know my stress tensor in terms of my metric, then by taking derivatives, I can get 2-point functions of my stress tensor. Okay, so there's a bit more details in this, but essentially this is what I do. I just think order by order in derivatives with every possible term I can write down made up of these guys, right, which are symmetric tensors. Okay, so at leading order, when there's no derivatives, that's called ideal hydrodynamics. I just have two terms. This guy here is the energy density, and this guy here is the pressure. Okay, and this delta, I think I forgot to include it on my slide. This delta, sorry to the people who missed that. This is just a projector, okay, which is transverse to the fluid velocity. Okay, so yeah, the ideal hydrodynamics is characterized by two transport coefficients, energy density and the pressure. Okay, and in 1 + 1 dimensions, in fact, if I now go to higher orders in the derivative expansion, really just thinking about what are all the possible structures that I can write down, which of them can appear in the 2-point functions, what I find is there's really only, at the end of the day, there's only two. Okay, and this is very different than in higher dimensions when there's hundreds and hundreds and hundreds of these things. Okay, so you have...
Just one question. I mean, to lowest order, I mean, this will be still entropy conserving this equation, or?
Yes, yeah.
And once the first order will give you dissipation, is that right? Or?
That's correct, yeah. So this thing, omega, right, this is some infinite series so I've written this in a kind of non-Lorentz covariant way, but it can be written in a Lorentz covariant way. So this is like the first dissipative correction. This is essentially the fluid viscosity. Okay, and then higher and higher orders, right? There's just more and more. Right? Every order of derivatives, there's more corrections. Okay, and then kappa or some other series.
Where does the KPC term appear in this series? I mean,
so here he's taking large C. Here he's taking large number of degrees of freedom, so now he's suppressing.
Okay.
Yeah. So that is important. I've taken large C kills the fluctuations, and what I'm going to say definitely relies on there being no fluctuations. Yeah.
But this equation is not just for large C. This is just 1 + 1 derivativistic hydro, right? As you write there, or?
I guess as I've written there, but what I'm going to say about 2-point functions and so on will
be large C.
Yeah.
But I guess if we want KPZ, we could take the earlier non-specific bit and then do nonlinear for certain hydrodynamics type of argument and have PV.
I guess so. Yeah.
Question. So this is sort of the conventional way, so to say, to do relativistic hydrodynamics. But in 1 + 1, the energy momentum tensor has like 3 components, right? T00, T11, T01. In a CFT, you remove the trace, right? Now you break and you're introducing this O, so you still have 3 components. You have 2 equations for the conservation, so essentially you can somehow try to postulate a 3rd equation for the trace.
And with the action I wrote down before, the trace is, the 2-point function of the trace is given by the 2-point function of this scalar operator that breaks conformally. So yeah, to say it in other words, in this theory, there's really only one 2-point function, right? They're all related to one another by word identities. Yeah, so and I'm going to use that in a second. Yeah. So it's kind of the kinematics of 2 dimensions are really very simplifying.
Yeah, we have in mind is like Isel-Stewart type description for the trace. Is that
is there I think there is, yeah.
So isn't the trace related to the 1-point function of the perturbing operator?
Exactly, yeah. So yeah. I don't know if that actually answers your question, but...
So that's the equation of state of the fluid, let's say. So you have to calculate that as function of epsilon and P. I mean, as function of the parameter that characterize 1p.
Of course, but it's a dynamical degree of freedom, right? If I were to throw into the theory, I would need one more dynamical equation.
No, so this you have two parameters, right, that characterize your state, and then these are the ones that are space-time dependent. Then you write two conservation laws.
No, I understand that, but I'm proposing an alternative to this picture.
Ah, yes.
Okay, so this here, right, assuming C is large, just fixes all the two-point functions of the stress tensor. And as I said, there's really only one two-point function of the stress tensor. The rest are all just related to it by word identities. And so I'm going to take that here to be the trace two-point function, okay, which is given by this thing here. Okay, so this capital omega is some infinite series in omega and k, where each term is a transport coefficient, and the same with the capital. Okay, so this is what the two-point function looks like. Let's look at the denominator. That tells us what the excitations of hydrodynamics are. Okay, if I look at very, very long wavelengths, then this guy is suppressed, and I see, right, the poles are just, sound waves traveling at the speed of sound, which I told you before. Okay, and so when I said at the very start, my hydro two-point function should be supported, right, along this trajectory, right, this is where that comes from. Okay, but really my theory of hydrodynamics is not just some freely propagating sound wave, right, I have this infinite series of corrections. Okay, and these are going to correct the dispersion relation of this and correct the two-point function. Those corrections are going to get bigger and bigger as you go further back in time. Okay, so if we really want to know what happens if we push this back in time, what we need to do is figure out what the values of these transport coefficients are. So what is the viscosity, right, from that action I started off with? Can I figure out what the viscosity is?
Excuse me, so how do you use that large C limit in these hydro discussions?
So I'm using it basically when I go from this expression, from the stress tensor to the two-point function. So I'm suppressing all fluctuations. Just as a kind of simple classical theory, this guy with respect to the space-time metric, and that gives me the two-point function. Okay, and so I'm going to give an argument that in fact we can calculate what these transport coefficients are at leading order at small lambda. Okay, so here's how it goes. So the first thing to, sorry.
Is derivation like you erase information about non-hydro sector, or?
Sorry?
In these formulas, you erase information about non-hydro sector, right?
For example, in this formula, yeah. So here we've lost, so the CFT will have all, deformed CFT will have all kind of short-lived excitations, right, which are not, well, let's say this. Information about them is hidden in these transport coefficients. Yeah. They are not, there's no other pole beside the hydro pole.
Yeah.
Sorry, there are a bunch of poles now.
Sorry?
Big omega, aren't there a bunch of?
Okay, I guess there'll be a bunch of poles, but they will be gapped, and so you probably can't trust them.
One very naive question. I mean, now you have two sound modes. There's no heat mode in such systems, is that right?
That's correct, yeah.
Because of special symmetry, or
There's two conservation laws. So
what?
two conservation laws, energy and momentum.
Okay.
The mass appears when you go to non-relativity.
Okay.
Okay, so how does this argument go? Well, the first thing to realize is just the CFT on its own, although I said hydrodynamic doesn't emerge, I mean, that's true, but in a sense, that's because the stress tensor in a 2D CFT obeys a theory of hydrodynamics, but basically just a trivial one. Okay, so if I take that hydrodynamic formula I had before, I set the energy density and the pressure to be those of a CFT, I turn off all of these transport coefficients, okay, and I take this other infinite set of transport coefficients and set it equal to 1. Okay, that gives me the stress tensor two-point function in a CFT. Okay, so this is a non-dissipative transport coefficient, so it's you get non-dissipative.
Doesn't it scale with the central charge?
Yeah, so I've kind of normalized the central charge out of kappa. Yeah. So for the experts, this thing here is basically the conformal anomaly. So I've normalized things so that. Okay, so in the CFT, my stress tensor two-point function is a hydrodynamic one, right, with And now what I'm going to do is assume when I break conformal symmetry, these transport hydrodynamics, I'll still have a hydrodynamic theory, but this isn't zero anymore, right? But now it's just some small order lambda squared number. Okay, so these things just get perturbatively corrected. Okay, and if I make that assumption, I can expand out the hydrodynamic 2-point function, a small lambda, okay, and the leading term, that's just a CFT 2-point function, okay, and then I get a correction, which is order lambda bar squared. Okay, and then there'll be more and more and more corrections. Okay, so that's one expression for the trace 2-point function. I can get a different expression using the word identity, so I can write the trace 2-point function in that QFT as the trace 2-point function in a CFT, right, plus this thing here. It's just using word identities. Okay, and then I can expand this thing out here, a small lambda, to get that the trace 2-point function is just the CFT, trace 2-point function, right, plus this specific correction, okay, where I just evaluate everything in the bracket in the CFT. In particular, this is the retarded 2-point function of a scalar in a thermal state of CFT. Okay, and we know what that is. Okay, this is the Fourier transform of some equation I wrote down near the start. It's just this guy here. Okay, so now we have two different expressions for this object, and the assumption now that comes in is we're going to assume that we've calculated this in two different order of limits. We're going to assume they commute. Right, so first of all, we took the hydro 2-point function, expanded it a small lambda. The second expression was we took the small lambda limit. Now we're going to expand that right in the hydro limit, a small omega and small k. Okay, and if we do that and then just match these things up to each other, what we get is the left-hand side, right? This just contains all of the transport coefficients. Okay, and the right-hand side is just the expansion in powers of omega and k of just some known function, right? And universal function, right? This is the same for any, right, 2D CFT. Okay. And so just by matching, order by order in pairs of omega and k, we can get expressions for all of these transport coefficients. So, for example, we can get that the correction to the speed of sound is given by this number here. Okay, this is what you get from conformal pairs, right? We know this is the right answer, as I had at the start of the talk, so this is kind of sanity check. Okay, the first term in omega, that's essentially the viscosity of the fluid, right? We get a specific formula for that, it's given by this. Okay, and you can just do this and get an expression for every single transport coefficient. Okay, when they get more and more complicated and less useful, right, their specific forms, but in principle you can do this.
Can you also derive the omega is originally depending on the omega and the capital omega depends on the frequency and momentum k, and do you obtain the such a omega and k dependent term?
Yeah, so this omega I'm writing here, this is a kind of an infinite series in a little omega and k. So this is, each term in that series is basically telling you a transport coefficient that arises at higher and higher in order in the derivative expansion. And so indeed, by expanding this right-hand side out just to higher and higher orders, you can read off omega 1, omega 2, omega 3, every single one, and all of the kappas as well. So in that sense, you have a formula for every single transport coefficient at leading order in small lambda.
So how do you use again the large central charge limit is to get the left-hand side?
So here, the large central, one way to see from here that the large central charge limit is crucial is that if I didn't, so the right-hand side here is going to be some basically analytic series in omega and k. If I didn't take the large central charge limit, my hydro 2-point function would have fluctuations in all kind of non-analytic terms. Right? And it would be clear just from comparing the left and right-hand side, the limits do not commute because right, they just look different.
And maybe so like conceptually, why do you expect the limits to commute? Central charge limit.
I don't think I have a great conceptual reason to give you. I mean, part of this I would say is kind of intuition of specific theories I'm used to, where it just kind of seems obvious to me that they should commute, but that's just my own particular intuition. And I think ultimately what it's going to come down to is, so if this really is the hydro 2-point function, then you should be able to get it by resumming that perturbation series I mentioned before. So I think essentially what's going to happen is when C is large, that perturbation series, as I said before, kind of factorizes into products of 2-point functions and simplifies in a big way. And I think that is to really prove the limits commute. So here there is no energy diffusion constant. So here there's only two conserved charges, which is the energy density and the momentum. And because of, it's kind of, yeah.
Okay, but why isn't there an energy diffusion constant? I'm confused. If there's a conserved energy, then I
By
expect...
Lorentz invariance.
Yes, because the Lorentz invariant theory, let's say the energy current is also a conserved charge.
Lorentz invariance, you can't get energy diffusion? I thought you could.
Sorry?
I thought you could get energy diffusion in a system that breaks Lorentz invariance because of the initial states it gives state.
So here energy does not diffuse. So the energy current is itself a conserved charge because of Lorentz invariance. And so the kind of two stress tensor conservation equations together, yeah. So the kind of analog of the energy diffusion constant would be the viscosity. That's what broadens, the kind of leading term that broadens out.
Thank you.
Yeah, but we can get expressions for all of the dissipative transport coefficients, right? I'm not secretly doing some equilibrium thing here. Okay, so right, we have all the transport coefficients, we have the two-point function, so the structure of the two-point function. So really, we have the two-point function, right? If you accept that these limits commute. Okay, and to me, at least anyway, this seems kind of like too good to be true, right? If you ever tried to take a quantum field theory and compute, right? Even a perturbative quantum field theory, compute like a single transport coefficient, it's horrendously complicated. And so seeing here we have, for a big class of theories, a universal expression for all of them seems kind of too good to be true. So let me give you some evidence about why this is not completely mad. Okay. So the first thing is, I mentioned this briefly before, right? I'm assuming these limits commute, right? It didn't have to be the case that I would get something, right, which matched up on either side. Okay, so indeed, if the central charge is not large, the limits don't commute. Okay. If they do commute, it's at least mathematically self-consistent. The second thing we can check is, if I just take a theory of hydrodynamics, right, and just give a bunch of random values to the transport coefficients, right, that theory will not always be sensible. Okay, for example, and what we'll check is within the regime of validity of our hydrodynamics, it is causal. Okay. Another thing we checked is there are some 1 plus 1D CFTs where you can really compute transport coefficients from first principles, right, without having to make these kind of commutation of limits arguments I'm assuming. So these are holographic theories. These have been, so the Hall viscosity, for example, is computed in holographic theories in the large C limit from kind of first principles arguments, 10 years ago or something. Okay, and you get exactly this number out. Okay, and finally, in the last couple of minutes, the other thing which we can do to kind of see that this makes sense is we can take this hydrodynamic theory, push it back to earlier and earlier times, and what we're going to see is it breaks down exactly where we expect it to break down. Okay, and there's going to be a nice simple physical picture we can see of why it breaks down. Okay. So to see how hydrodynamics breaks down, what we're going to do is take this sound wave, okay, which appears in the denominator of the two-point function. It has some dispersion relation, okay, which is some series in K. As Mikael was telling us this morning, well, in some cases, and certainly in this case, what we're going to find is this series has a finite radius of convergence. Okay, so if you try and push this to like very, if you try and push this to large wave numbers, right, to short distances, right, you're going to see the series fails to converge, right, and that's telling you hydrodynamics is breaking down. Okay, and to see where this series converges, what we can do is take this thing we had, resum it. Right, we can resum the lambda squared correction to the sound wave, okay, and we get this complicated little thing here. These gamma functions have poles, okay, and these poles are going to give us the radius of convergence of this series, okay, and so we can read off exactly where this series stops converging, okay, and it's at wave numbers which are equal to pi times the temperature times delta, the dimension of this operator. Okay, so if we just Fourier transform things, what we can see is this produces, kind of out of control corrections on the sound cone at exactly this time scale here, right? So hydrodynamics is getting out of control as we go to early times, exactly the time we expect it to get out of control. Okay. Okay, and going to Fourier space, there's a very nice picture of what is causing hydrodynamics to break down at very, very early times. is a picture similar to what Michael had this morning. So here I'm showing complex frequency plane, okay, and then these dots here show the poles of the two-point function of the stress tensor. So these are showing us like the excitations of the theory that carry energy. So when K is very, very small, so I'm looking at very long distances, right? I have two hydrodynamic modes. These are my sound modes, okay? And then I have a huge gap, okay? And what I have, right, much shorter lived excitations, I have basically thermal excitations of the scalar operator in the CFT. Okay, and I know exactly what their dispersion relations are as well. Okay, so very long distances, I have my long-lived hydro modes, okay, and then I have these much shorter lived thermal excitations in the CFT.
All the polars located in the lower half plane?
That's correct, yeah. Okay, and then what I can do is just say, well, what happens if I increase K? Okay, what happens to all these modes? And what I'll find is, right, I know what the dispersion relation of this thing is because I know hydrodynamics to all orders. I can follow exactly where it goes. Okay, I know to leading order and lambda what the dispersion relations of these guys are because they just come from the 2D CFT. And what I can see is, as I increase K, up to this specific value here, okay, the hydro mode, right, this guy's getting shorter and shorter lived. The CFT mode, one of the thermal excitations of the CFT is getting shorter and shorter lived, and exactly that wave number, these two guys collide with one another, right? And that is telling you hydrodynamics is broken down, right? Because you have these excitations here, right, which are not included in hydrodynamics, and they're becoming just as important as your sound waves at those distances. Okay, and so really even quantitatively, right, this radius of convergence
So in your analysis, can you explicitly find that such a non-hydrodynamic pole?
No. So what I've done here is I've said when lambda bar is very, very small, what I expect is I'm going to have something that my two-point functions of the stress tensor, I'm going to have this hydrodynamic thing that I can resum from a minute ago, and I'm also going to have these short-lived scalar excitations, and when lambda bar is very, very small, the dispersion relations of those guys are just going to look like those of a CFT. So here, this is just the CFT result for the dispersion relations of those guys.
But you have the formula for the capital omega, including the frequency-dependent corrections.
Yeah.
Then if you find that the denominator to be 0, then if capital omega have the higher omega correction, you may have the additional pole.
So I haven't checked actually quantitatively if that works out. I think maybe it won't, right? I think taking this hydrodynamic limit, we're kind of losing some of that information, but I'm not 100% sure. Okay, yeah, I guess I'm already over time, so let me just stop with a kind of summary. So the summary is that 1 plus 1 dimensional quantum field theories at very high temperatures, very low temperatures thermalize slowly, right? And that's how long they take to thermalize. Okay. From the early time perspective, the reason they thermalize is conformal perturbation theory is breaking down, right, because of this unsuppressed exchange of stress tensors near the light cone, right, and that is what causes hydrodynamics to emerge. Okay, and I guess I didn't say this before, but let me emphasize it here, right? This is very generic, right? CFT, it has a stress tensor, this will happen. So, right, that's a nice thing about this, and it's kind of an expected thing, is we expect thermalization to happen in general, right? And we can see here, it doesn't really depend on the CFT you start with, right? It's always going to happen. And then the second conclusion was that this conformal perturbation theory breakdown allows for hydrodynamics to emerge, and when the central charge of the CFT is very, very large, we can get explicit universal expressions for all the transport coefficients that emerge. Let me stop there and just put up. I have lots of things I'm still interested in about this, so let me just leave them on there so that I don't take even more time. Thank you.
I have a question to the early part of was a very nice presentation. To the early part of your lecture, so you start from this conformal field theory, and then you take a perturbation where integral over dx of x. Couldn't it be that the conformal field plus the perturbation is still conformal invariant?
I guess so. So yeah, if I turned on a perturbation which was exactly marginal, that would be the case. So in what I did, I'm assuming the scaling dimension of this operator is between 0 and 2, which means for sure it breaks conformal symmetry. So I'm assuming that it breaks conformal symmetry. If you don't do that, then if you have an exactly marginal operator, then I would not expect thermalization to happen.
If you chose a perturbation that did explicitly break Lorentz symmetry, like for example, if you took an O but you modulated it with something that varied in space, do you think you could see the emergence of energy diffusion in this formalism? Or
Maybe. I think certainly what we've done is kind of the simplest version of this kind of game, let's say, and I think more complicated versions could be played. So one thing we haven't done, I have it on the first line here. So ideally, what you would like to do is I had this perturbation theory argument, and essentially what I'm saying is if you could resum that, you would get the hydrodynamic two-point function, right? And that would really be a way to derive hydrodynamics from the quantum field theory. And we didn't quite manage to do that, but I do believe, I don't think it's a pipe dream. I really think it's possible. And whether it's possible to do that, right, also including Lorentz invariance breaking and so on, I don't really know, but maybe.
Maybe you already said that, but I missed. What happens if you add an integrable perturbation and so you still have infinite symmetries, but
So what I'm saying, when towards the start I use this kind of generic, and what I really mean by that is non-integrable. So certainly if you take a CFT and you turn on some integrable deformation, what I'm saying is does not apply, right? The kind of conventional hydrodynamics that I'm talking about here would not emerge, right? Because there's all kind of other conserved charges. But yeah, so I think, I mean, certainly I would, let me just say that,
So there's one thing that I find confusing, but maybe it's trivial for you to understand. So if I think about high number dimensions, right, so like three-dimensional CFTs and higher, then I have hydro, right? If I break conformal symmetry, at least like in holography, I can do the calculations, and I see that the time for applicability of hydrodynamics coming from the correction breaking conformal symmetry is going to be just like a small change with respect to, say, time set by the temperatures. It's going to be like 1/t plus some correction that is given by the relevant coupling, right?
Yeah.
Over here, somehow, without the deformation, you don't really have hydrodynamics, right?
Yes.
And so like, what I find puzzling is that this correction gives you the time for applicability of hydrodynamics that scales as like a weak coupling estimates, right?
Yes.
Or thermalization timescales, shear viscosity, etc., right?
Yeah. I think the way to think about it is that this is special to 1 + 1 dimensional CFT. So for a 2 + 1 dimensional CFT in the thermal state, it's hydrodynamic, right?
Yeah.
And there's just kind of no the thermal, right? Let's say it's strongly correlated. The thermalization time is going to be the inverse temperature, and if you do some kind of small perturbation to your system, it's not going to change that thermalization time. So really, what's important here is that in a 2D, specifically a 2D CFT, right, the symmetries are so constraining that even the thermal state, right, the thermalization time is infinite. Or if you like to think about it this way, the transport coefficients are all 0. And so then turning on a small correction basically tells you, right, the leading term in every single transport coefficient.
But maybe then, like, I mean, okay, it's again like a very naive comment. Maybe then, like this logic is at best in high number of dimensions applicable to free theories, right?
Sorry, can you say it again?
In higher number of dimensions, this logic is applicable then to free theories, right?
I mean, I get, yeah.
Similar. It looks very similar to if I look at, say, a perturbative calculation of the transport, right? What I would get is that the shear viscosity is proportional to 1/the coupling squared.
Here it's proportional to coupling. Here it's proportional to coupling squared, not to 1/coupling squared. So that's a big difference. It's not singular, which is kind of.
Oh, okay. So it's going to 0.
It's going to 0 instead of going to infinity.
Bulk is different from shear.
Oh, I see. Oh, okay.
Yeah.
But this is
You know, bulk has logs, and it's still quite different.
But the time of applicability diverges, right?
for example, if you look at this derivation of hydrodynamics using 14 moments, right? There you have that the relaxation time diverges with decoupling, and it's quite similar to your.
That is similar.
Yeah, this is what I had meant. Yeah. But thanks for the clarification.
Maybe we can continue on. You had a quick question. We can continue discussion afterwards. Thank you. Thank you very much.